Hi Year 10, and today we're going to look at another required practical, and we're going to be doing one a day. We're looking at specific heat capacity. Now this one pretty much always comes up because it is quite confusing, but it doesn't need to be. So hopefully today will help you give a better understanding. You probably did this practical and it didn't work particularly well in school. No reflection on you guys, however, that's one of the things that happens with this practical. So what do they want you to know? What is meant by specific heat capacity of a substance? How to calculate the energy changes that occur when an object changes temperature? How the mass of a substance affects how quickly its temperature changes and when it is heated? How to measure specific heat capacity of a substance? And this practical can be found in your online textbook. So you can use your caboodle and you can find it on pages 26 to 27 in the trilogy physics. Okay, and there's some examples of how we use this information about specific heat capacity to work out and manipulate and apply the science. So the equipment is quite simple. You probably did this in class and it looks a lot more daunting because there's lots of wires, but simply what we've got is a joule meter, which we're going to be using to heat up our measure the energy that is being supplied to the heater. We've got a thermometer that's going to be measuring our rise of temperature, and we've got an aluminium block, and that block can be of any material. So the odds are that in an exam they give you a different material, but it's essentially doing the same thing as the aluminium block. And then it's all covered in a big layer of insulation to keep any heat that is given to the heater, to the metal block, retained in that space, and none of it is lost to its environment. So specific heat capacity is the amount of energy needs to raise the temperature of 1 kilogram of any material by 1 degree C. So we have to try and work out, the point of this practical is to find the specific heat capacity of a material. And you need to heat it up and work out how much energy has gone in. And if you haven't got a joule meter, but you do have an ammeter, a voltmeter, or a power meter, you can work this out. And again, we can use those two equations that we have talked about before. So the example apparatus, which I've just sort of talked through a little bit, is the joule meter measures the energy going in joules, which is our unit of energy. Heater heats the block. Insulation does exactly what it says on the can, stops the heat escaping to the atmosphere or its environment, surroundings. And the temperature measures the thermometer measures the temperature rise. So here we come to our practical, and we have our independent variable, and the independent variable is the temperature of the metal block. And we will be measuring that at the start and at the finish. The dependent variable is going to be the energy supplied to the metal block by heating. And control variables, the mass of the block is the mass of the metal block. Okay, now that shouldn't change throughout your experiment. However, if you wanted to repeat the experiment, you'd try and use the same block. So this idea of an immersion heater here, it sits inside. So you would have be given a cylinder of aluminium with 2 holes in it, and those 2 holes is one goes inside your immersion heater, the other goes into your thermometer. And you would have found that the thermometer hole had a tiny bit of oil in the bottom, and that was to try and increase the contact between the bulb of the thermometer and the block of metal. So you've got 2 different sets up here. The first one with a voltmeter and an ammeter, and the second one with a joule meter. Now there needs to be a risk assessment here because you are using a number of things that could be risky. So the hot immersion heater and metal block could potentially burn you. So you do not switch the heater on until it's placed on the block. You do not touch it when switched on, and you allow it time to cool down before putting away. There are other things that you may want to consider here. The fact that the block should be sat on a heat resistant material. There is also electricity involved, so you need to consider the risk of electric shock. So method. Now, if you're not familiar with this method, I would try and summarise it into the following bullet points. Now, I always find when I'm looking at these methods, and this is something I've been doing a little bit more of recently, is I summarise it into maybe try and think about each bullet point as a section of maybe 4 or 5 words. Because, to be honest, you trying to remember that whole sentence is going to be quite tricky. So, either do yourself a little cartoon sketch. Number 1, weigh the block. Okay? Right? Number 2, insulate block. Number 3, set up the equipment shown. Number 4, add the thermometer, measure the temperature. Okay? Number 5, switch on, start timing. Number 6, record the current and potential difference. Okay, or it could be record the initial score or the joule meter. Number 7, watch the reading on the thermometer and record the temperature every 60 seconds for 10 minutes. Okay, then number 8, when it's reached 15 degrees centigrade above, you start, switch it off. Okay, record the temperature again. It's that simple. So don't feel that you have to write everything down, but what you do need to be able to do is record it in nice quick successions. Okay. Now, the demo can be watched at bbc.co.uk. Alright, and you can see that being done. It's not the world's most exciting practical, but it's one that they want you to know about because there has huge potential for this practical, and it does affect a whole range of everyday science, and we'll talk about that in a minute. So specific heat capacity, again, we've talked about what this means, and the block has a mass of a kilogram, and you usually find it's got a nice round number. Okay, and we're going to assume that the block was running for 10 minutes, therefore that's 600 seconds. So using these as results, we're going to use energy transferred equals power times time. So there are multiple steps, and I just want to point out for those of you who are thinking, oh my god, what is she on about here? However, this would be worth six marks on a higher paper. However, for those of you who love a bit of maths, and I do love a bit of maths, this is easy marks, because if you know your equations, you can just pull it out of the hat and bish bosh bash, you have got 6 easy marks. So the first equation here is E equals P times T, which is E is equal to energy transferred equals power times time. And therefore we do 50 times 600 equals 30,000 joules, which that gives me my Q, which is energy supplied or energy transferred. So energy transferred is equal to M, which is the mass of the block, C, which is capacity. This little triangle is called delta, and that means change. And the last little circle with looks like a 0 with a line through it is called theta, but that's just change in temperature. Now, to work out the specific heat capacity, we need to rearrange that equation to make C the subject. So what we then do is put C to one side. We've then put change in Q over mass times change in temperature. So energy divided by mass, which is 1, and change in temperature, which is 44 minus 15, and that gives me a specific heat capacity of 1034 joules per kilogram per degree C. Make sure that we're aware of those units, because those units will also be a big point scorer. So the actual value for specific heat capacity of aluminium is about 900 joules per kilogram, and the calculated value does not match it exactly, but it's about in the right sort of ballpark. So we're going to explain now why there could be a discrepancy between your results and the results achieved in what we call a clinical scientific setting. So what could they ask you about this? So they might ask you, why do you need to insulate the block? And you need to be talking about stopping heat losses to the atmosphere so that all heat is retained by the block and can be measured. Why is your answer not the true value? Well, because not all the heat is going to be transferred to the block, and all those and through to the thermometer. So the thermometer tends to poke out the top of the insulation, and that will be a conductor. Glass is a conductor. Okay, remember that. Think right back to P1 when we're talking about conductors and insulators. So why is the temperature increase slower at first? Now, it takes quite a lot of time for the temperature to start to heat up and for the heat to reach the thermometer. All right, and then it may not be the block of metal. You could use a kettle to heat the amount of water in another way using a heating element. And the last bit that they really want to talk about is something called resolution. So what is the resolution of temperature measurements? And that basically means how small were the increments on the thermometer. So the resolution of your temperature, if your thermometer, does it measure in degrees, does it measure in half a degree? That's important. And they could ask you about repeatability and why you would want to do this more than once. And they want you to think about uncertainty. How certain or uncertain are you that you are closer to the true value? So the results need to be plotted into a suitable table. And time is in the first column and temperature is in the second column. And then my evaluation, what could you conclude from this? All experiments are subject to the same amount of experimental error due to an inaccurate measurement or variables that cannot be controlled, or in this case, not all the heat from the immersion heater will be heating up the aluminium block. Some of it could be lost to its surroundings. And I keep mentioning this because that is the biggest cause of error in this practical. If you were doing it completely sealed and using digital probes, you could have nothing protruding at the top of the block and have it all nice and sealed and compact and then doubly insulated. That's maybe an improvement that you may want to mention. So the more energy has to be transferred than is needed for the block alone. And as some of it is transferred to its surroundings. Now think back, energy cannot be created or destroyed. It can only be transferred. So that energy has had to go somewhere. And this causes the calculated specific heat capacity to be higher than the 1 kilogram of aluminium alone. Okay? So below some useful links for this topic.